Good afternoon, all my AP Chem students. We are going to take our first podcast here for Chapter 16, and it's going to be on spontaneity and entropy and free energy. These are going to be some new terms to you that we did not talk about in General Chem. However, they're things that you know about, just haven't really thought about. So our first law of thermodynamics says that energy cannot be created nor destroyed. And so that means that our energy in the universe is going to be conserved. So some of you that drove a car today, you were burning some methane and you got some energy output on that. It's an exothermic reaction. But how that energy remained constant, but there's no hint as to why that process occurs and why it happens in a given direction. You drop a book. You have potential energy stored in the book. It falls to the floor. There's kinetic energy transfer, and then it goes back into potential. We have the same quantity of energy before and after, and it's still that textbook, but again, there's still no hint as to why that reaction happens. And that's this chapter, spontaneity. So to keep in line that the first law of thermodynamics is saying that energy in the universe is constant. So now we're going to talk about entropy and spontaneous process. So in entropy, the formula is S, and it's a measure of molecular randomness or disorder. So for instance, if I were to put a piece of ice in your hand, it's going to melt. You can't stop it from melting unless you put it back into the freezer, but it is going to spontaneously melt. If you take a deck of cards and you open up a brand new deck of cards for the card sharks in the room, you know that they come in nice order of suits, and they are in an exact order every deck that you open. You toss them up into the air and you have lots of entropy because you have tons of randomness in those cards, and it's going to take a lot of energy on your part to get them back into that nice order. Maybe just like how your mom says you need to put your bedroom back in order every once in a while, you can throw at her that, you know, I'm studying entropy right now, and that's what I need to do in my bedroom. See what she gets with that. Okay, so a spontaneous process is one that occurs without outside intervention. Just like we talked about, that ice is going to melt. It's possible to occur at any rate. Yes, can I speed up that melting? Can I slow it down? Absolutely. Speed, though, we're going to talk about in kinetics. So right now, we're just going to say that yes, it's going to happen. And then we can increase the entropy in the universe. So here, we need to remember that we can increase it. We can increase this randomness in our universe, whereas when we're talking about the first law of thermodynamics, the energy is remaining constant. So in nature, you need to think about that in nature, this is the easiest thing for it to happen. It doesn't want low entropy. It wants high entropy. It's easier for it to be in a state of disorder. If we throw those cards up again, it would take a lot of energy to get it back into order. And so nature wants things in terms of low energy. So a lot of times that's going to be at high entropy. A lot of craziness going on in the gaseous phase, for instance. And so there's lots of entropy, but it is lower amount of energy. So entropy is a thermodynamic function that describes the number of possible arrangements, the positional probability for a given system. Now, this is the driving force in entropy. This is the driving force, is how many positions can you get some of the molecules in. So if we take a look at this diagram, the expansion of an ideal gas into evacuated bulb, you guys can take a look that if I were to open this valve, and you can see over here that I have a vacuum, I hope that you're thinking that those molecules are just going to rush right in here, and they are going to try to make it even, as you see in the picture down below. So is this going to happen spontaneously? Yes, it's going to be spontaneous. You are not going to be able to stop that movement. So the gas has a desire to have this uniform distribution because it wants to be uniform, because it requires less energy to be in this state. Now think about the amount of energy that it would take for this system right here to look like that one again. It would take a ton of energy to do that, and nature is not going to do that. And so whatever it can do to create a situation that there's less energy, nature is going to do that. Okay, so now it all has to do with the positional probability, like we said, is the driving force. So it depends on the amount of randomness in the system. Now, as you have heard me say 100 times, be the molecule, be the molecule, be the molecule. So if you are a solid, you are very closely packed, you don't have a lot of movement, you don't have a lot of places you can go, and so you have low entropy. And then you have liquids, you have a little bit more movement, and then you have gas. You have that craziness with all that movement that you can do, that you have a lot of entropy in that situation, because there's a lot more positional probability of places that you can be. So how we do this and how we classify this is the same thing with enthalpy. Remember, that's our change in heat, is that we have signs for this. So a positive change in entropy means that it has increased entropy. This is more randomness. So this is where there's more positional probability of places that an atom or a molecule can be. And then if it decreases, it's a negative change in entropy, so it's decreased entropy. So just to give you a couple examples, if I were to say that I'm going from a solid to a liquid, I hope that you would think that there's a little more space with the liquid molecules, so this is going to be an increase in entropy. If I flip it around and go in the opposite direction, going from a liquid to a solid, I would have decrease in entropy because it's becoming more ordered. So if you can say something's becoming more ordered, then it's going to be a decrease in entropy. All right, that's the end of this section. I have the next video listed up, and it'll go pretty quickly. And then we will talk about section 16.4 and the rest of the unit in class. And I see there's some sample exercises. We are actually going to discuss these in class to make sure that you are understanding the theory and be able to apply them to these questions. All right, you guys have a wonderful night, and I can't wait to see you in class.